The enthalpy of fusion, also known as heat of fusion, is the change in enthalpy resulting from heating a given quantity of a substance to change its state from a solid to a liquid. The temperature at which this occurs is the melting point. The enthalpy of fusion is a latent heat, because during melting the introduction of heat cannot be observed as a temperature change, as the temperature remains constant during the process. The latent heat of fusion is the enthalpy change of any amount of substance when it melts. When the heat of fusion is referenced to a unit of mass, it is usually called the specific heat of fusion, while the molar heat of fusion refers to the enthalpy change per amount of substance in moles. The liquid phase has a higher internal energy than the solid phase. This means energy must be supplied to a solid in order to melt it, and energy is released from a liquid when it freezes. Because the molecules in the liquid experience weaker intermolecular forces and so have a higher potential energy. When liquid water is cooled, its temperature falls steadily until it drops just below the line of freezing point of 0 degrees Celsius. The temperature then remains constant at the freezing point while the water crystallizes. Once the water is completely frozen, its temperature continues to fall. The enthalpy of fusion is almost always a positive quantity. Helium is the only known exception. Helium-3 has a negative enthalpy of fusion at temperatures below 0.3 K. Helium-4 also has a very slightly negative enthalpy of fusion below 0.8 K. This means that, at appropriate constant pressures, these substances freeze with the addition of heat. Reference values of common substances. These values are mostly from the CRC Handbook of Chemistry and Physics, 62nd edition. The conversion between cal per gram and J per gram in the above table uses the thermochemical calorie equals 4.184 joules rather than the international steam table. Calorie equals 4.1868 joules. Examples. 1. To heat 1 kg of water from 283.15 K to 303.15 K requires 83.6 kilojoules. However, to melt ice also requires energy. To heat ice from 273.15 K to water at 293.15 K requires 333.55 J per gram equals 333.55 kilojoules per kilogram equals 333.55 kilojoules for 1 kilogram of ice to melt plus 4.18 J times 20 K equals 4.18 kilojoules times 20 K equals 83.6 kilojoules for 1 kilogram of water. To increase in temperature by 20 K equals 417.15 kilojoules. Thus 1 part ice at 0 degrees Celsius will cool almost exactly 4 parts water from 20 degrees Celsius to 0 degrees Celsius. 2. Silicon has a heat of fusion of 50.21 kilojoules per mole. 50 kilowatts of power can supply the energy required to melt about 100 kilograms of silicon in 1 hour, after it is brought to the melting point temperature. 50 kilowatts equals 50 kilojoules per second equals 180,000 kilojoules, H 180,000 kilojoules, H asterisk 50.21 kilojoules asterisk 28 GSI asterisk 1 kgsi 1000 GSI equals 100.4 kilograms. H solubility prediction. The heat of fusion can also be used to predict solubility for solids in liquids. Provided an ideal solution is obtained, the mole fraction of solute at saturation is a function of the heat of fusion, the melting point of the solid and the temperature of the solution. Here, R is the gas constant. For example, the solubility of paracetamol in water at 298 K is predicted to be. This equals to a solubility in grams per liter of, which is a deviation from the real solubility of 11%. This error can be reduced when an additional heat capacity parameter is taken into account. Proof at equilibrium, the chemical potentials for the pure solvent and pure solid are identical, or with the gas constant and the temperature. Rearranging gives And since the heat of fusion being the difference in chemical potential between the pure liquid and the pure solid, it follows that application of the Gibbs-Helmholtz equation ultimately gives, and with integration, the end result is obtained.